So today is sort of the culmination, the big finale of all this stuff. Okay? So we've been looking at position time graphs, we looked at displacement, we looked at velocity, we moved into velocity time graphs where we found average acceleration. So now we're going to do sort of likely what is the most challenging one. And I'm going to sort of summarize and wrap it all up for you. Okay? So you might remember from Friday, I guess, we found average acceleration, and I don't think we did instantaneous acceleration. Okay? And we found the slopes of these lines. We found out that the slope of the VT graph is the acceleration, and we dealt with straight line segments. And then I asked you questions like, when is it moving forward, when is it stopped, and all that. And we had a little trouble with that, but I think we're good now. Right? Okay, so now find this page in that handout. I think it's page 2 if I'm not mistaken. Graph, page 2. Okay? And let's talk about displacement on a VT graph. And you might remember I said one of the first things you should do is you should double check what kind of graph you're dealing with. And you need one, don't you, Sarah? Should be back there in the box. So, as I was saying, you need to ensure that you know what kind of graph you're dealing with, because what kind of graph you have determines the steps that you have to proceed with a certain question. Alright, so the rule is this. Displacement on a VT graph is determined by calculating the area between the graph and the time coordinate over the time interval in question. That's the main line right there. Calculating the area between the graph and the time coordinate. And I always regret having the word time coordinate in there. I would prefer to say time axis. So it's the area between the graph and the axis. Now you might hear me say area under the graph. That's the calculus in me speaking out. Okay? In calculus, they tend to only deal with graphs that are above. Okay? We're going to deal with above and below. So there's a special thing you have to be careful of. So it's the area, again, between the graph and the axis. In the example, the displacement for the time interval A between 0 and 2 seconds would be equal to the area of the triangle formed by the graph and the time coordinate. Okay, so for example, right here, right? We're talking about this interval here. What's the instantaneous velocity at the start? How fast is this going at the start of this interval? 0. And it ends up going at 4. Now, some people might say, well, if it's going 4 meters per second for 2 seconds, well, then it should go a distance of 8 meters. But you'd be wrong. Is it going 4 meters per second the entire time? No, in fact, it's only at the very last instant that it reaches 4, right? It starts off at 0. At some point, it's going 1, maybe 2, maybe 3, maybe 4, right? Okay? So, we find the area. Now, this is a triangle, and you should remember from about grade 5 or so that the area of a triangle is half the base times the height, right? So the base is from 0 to 2, so the base is 2 seconds, and the height is from 0 to 4, so the height is 4, and if you include units, that's 2 seconds and 4 meters per second. And if you multiply that all out, 1/2 of 2 is? 1/2 of 2 is 1, times 4 is 4, right? And if you multiply the units out, seconds times meters per second, the units seconds cancel, and you're left with meters. If you're in the calculus world, this little process is called integration. You can try to remember that for next year advanced math. Integration. Okay? If more than one time interval is to be used in the calculation of displacement, then the total displacement is simply the sum of the displacements of each time interval. In other words, you have to do each one individually and then just add them up. Okay? So, if the displacement for intervals A and B were to be calculated, the following technique would be used. So, interval B is this one here. You'll notice that here, the shape is not a triangle. It's a what shape? What shape is this? This blue one here. It's a rectangle, right? So, do I go half the base times the height? No, I go base times height or length times width, right? So what is the length here? What is the base? It's from 2 to 5, so that's a distance of 3. Now here you got to be careful because some people might say that the height is 2, but it's actually 4 because we're going up by 2s, right? So it's 3 over and 4 up, so that's a displacement of 12, right? 3 times 4 is 12. The original one was 4. You add them together, 16 meters. Okay? It goes 4 here, 12 there for a total of 16. Does that make sense? Yeah, I'm speaking English? Excellent. Guess what's coming up? The French. No Francais. What if it's below? I do have to tell you this. If the graph is below the time coordinate, the time axis, then the displacement is negative. It's going to the left. The displacement for the time interval d would be calculated as shown below. So d is this one here. Again, it's a triangle, okay? So I'm talking about this area here. I would encourage you to shade that in. Okay? Now, I always question, should I show them the most common mistake and tell them not to do it, or should I not show them because sometimes showing them encourages them to do it? Don't show you? Okay, I won't show you the common mistake. I will just remind you, in this case here, it's the area between the graph up to the axis, right? It's like above, right? Okay, so from 7 to what looks like to be 8.5, so that's a base of 1.5. And then it's down to minus 3, so 1.5 times 3. So it's half because it's triangle. Base is 1.5. Height is minus 3, and so you get an overall displacement of minus 2.25. It's going to the left. 2.25. Does that make sense? Okay? Let's do a little bit of clicker practice. So I'm going to ask you to find the displacements of all remaining intervals. Interval C, interval E, and interval F. And I'll take a few moments and let you do that. Okay, so C is highlighted here. C is from 5 to 7. E is down here, the flat portion. F is the next one there. Is there a question 4? No, there's not. So you've only got 3 to do. I'll pause and I'll do my attendance. Okay, so the displacement for interval E. It looks like I got several answers. Maybe some of you put 4.0, I don't know. Okay, but it looks like I got lots of answers there. So again, it's the area of a triangle. And the triangle is from 5 to 7. So the base is, it's 1/2 because it's a triangle. The base is 2 from 5 to 7, and the height is from 0 to 4. So it's 1/2 of 2 is 1 times 4 is 4. What do you know? It's 4 meters. It's exactly the same area as that one. Right? Interval E. Notice that it's a rectangle. And it's from 8.5 to 11. That would be a distance of 2.5. And the height is down to minus 3. So 2.5 times minus 3 is going to be minus 7.5. And it has to be negative. It's below. Okay? Interval F, again, is a triangle. 1/2 the base times the height. The base is from 11 to 14. That's a distance of 3. The height is from 0 down to minus 3. So 1/2 of 3 times minus 3, which would be minus 4.5. Hopefully that's the right answer. Minus 4.5. Excellent. Okay. How would I find the total displacement for the whole trip? Add them all up. Is it going to be 0? I mean, doesn't it end up right where it starts? We don't know where it ends up. We just know that it starts at 0 meters per second and it ends at 0 meters per second, right? Remember, this is a graph of velocity. You have to twist your mind a little bit. You got to think of it. It's a velocity time graph. We don't know exactly. In fact, I've never actually figured out what the total displacement is. Okay, now let's talk about average velocity. We already talked about average acceleration, but what about average velocity? So, whenever the average velocity is to be calculated under any circumstance with a VT graph, it must be done using the formula V bar equals d over t. Now that's a formula that you guys got, I'm thinking, in grade 10. V bar equals d over t, and we've used it a few times already, right? Where the displacement is calculated from the VT graph using the area under the curve technique. In other words, you got to do what you just did to find the d value, the displacement, and then simply divide by the time. So, the average velocity for the intervals A and B, so from 0 to 5 seconds. We already calculated the displacements. We said it was 1/2 times 2 times 4. We got 4 for this guy here, that triangle. We got 12 for the rectangle, which is a total of 16. Right? So all of this is 16 meters. It happens in how many seconds? 5. So 16 divided by 5. And the average velocity is 3.2 meters per second. Okay? Now if you look at this, here's a common misunderstanding. People will say, well, the initial velocity was 0, right? The initial velocity was 0, and the final velocity was 4, right? We ended there. Final velocity is 4. Well, the average of 0 and 4 is 2, Mr. Bennett. Is that not true?
Yeah.
It is true. So why doesn't it work? Say again? Not the whole time, but we were traveling 4 meters per second for a much longer time than we were traveling 0. In fact, we weren't even traveling 0 for very long, right? It was just an instant. And then it went to 1 and 2 and 3 and 4. We've got a much longer period of time here at 4. That's why the average is 3.2, right? If I jump in my car and I start my stopwatch and it's 0, and I drive all the way to Brandon at exactly 100, speed through the park, do I go 0 to 100? My average velocity is 50? I don't think so, right? My average velocity would be a little less than 100, right? Because I go at 100 for a much longer period of time. Okay, so now your job is to determine the average velocity for the entire trip. So you, in fact, do have to add up all the displacements, and then you're going to divide by the total time. Okay, so what did you get for a total displacement? My answer is 0.4. Looks like a few people got that. 0.4. So, what were those values? I think it's 4 and 12 and 4, and what was that one? Negative what? 2.25. And then the rectangle at the bottom? Negative 7.5. And then this one here, Jason?
Negative 4.5.
Okay, so you add those all up, and what do you get?
5.75.
5.75? And then you divide by 16, and you should get 14, right? And you have to be able to round properly. Okay, so now let's talk about instantaneous velocity. Now this is the easiest one of the day. Don't get this one wrong. Easiest one. Instantaneous velocity. They're asking how fast is it going at a specific instant or time. Right, Cameron?
Right.
Yeah, leave Mom alone. She's busy. Okay, so how fast is it going at 6 seconds? Well, right here, you just do what? Read it off the graph. It's a graph of velocity. Instantaneous velocity, just read it off the graph. And so, everyone's going to get this one right. How fast is it going at 13 seconds? After I've just told you how to find instantaneous velocity from a graph. How fast is it going here at 13 seconds? Okay, and the answer is almost everyone. -1. Read it off the graph, right? Minus 1. Okay, now, what about instantaneous acceleration? Instantaneous acceleration is determined the same way off a VT graph that V-inst was determined off a PT graph. That is, find the slope of the VT graph. You may need to draw a tangent line if the graph is curved. If it's not curved, just pick any 2 points. Does it matter what points? Any 2 points on the line. So, for example, instantaneous acceleration at 6 seconds, right there. How fast is it going? We're talking about the slope, right? It's the slope, average acceleration, sorry, instantaneous acceleration of a VT graph. So we're going to find the slope. So that's going to be 0 is the y, minus 4, all over 7 minus 5. That's going to be minus 4 over 2, or minus 2 meters per second squared. Minus 2 meters per second squared. So now I ask you, what is the instantaneous velocity here at 12 seconds? Oh, is this going to be the one? Is everyone going to get it? The answer is 1. Correct answer is 1. Let's have a look. Why is it 1? The y value here is 0. Subtract. That's minus 3. Subtract minus 3. It goes up 3, does it not? 1, 2, 3. Over. The x value is 14. Here the x value is 11. 14 minus 11 is 3. 3 over 3 is 1. You've got to be able to do them that fast, you guys. 1 what? Meter per second squared. Now, what would you do if it was sloped? If it was a curved line? You're going to have to find a tangent line, find 2 points, any 2 points, find the slope. Okay. Now, these next 2 pages are mega important. Okay? I would suggest you put them flat so you can see both at the same time. Okay? This is basically your cheat sheet for everything you need to know about graphs. So listen carefully. Okay? Because this is, I'm basically making a cheat sheet here for you. So, let's talk about the left-hand side is position time graphs, right? Does it say position time graph at the top of yours?
Yeah.
Does it say it on the next page? It does. Excellent. Okay. Do you guys have a line down the middle? You do now. I used to make kids draw a line. So, down the left-hand side is all position time graphs. Here's how to do it. If you have a position time graph and you're asked to find displacement, you simply read the final positions off the graph. Like so. Right? That would be xf, that would be xi, and you subtract them. Right? You're asked to find displacement. So you find the initial position, xi, you find the final position, xf, and you subtract them. Some people like having that little graph there as a little visual reminder. If you have a position time graph and you're asked to find average velocity, how do you do it? Well, there's 2 types. You could have a straight line graph, or you could have a curved line graph. And if it's a straight line graph, you simply find the slope. So again, here's the graph for that. You find the slope. If it's a curved line graph, what do you do? You find the slope of a line drawn between the points of interest, because we're talking about average velocity. Okay? So you pick the points that are at the end of the interval, draw a line, find the slope of that line. What about instantaneous velocity? If it's a straight line graph, we need to find what it is at an instant. How do you find the slope at an instant? Well, if it's a straight line, you just take the slope of the line, right? Any 2 points. Any 2 points, and find the slope. If it's a curved line graph, and you're asked to find instantaneous velocity, How fast is it going right there? You're asked to find the slope. Slope of a curved line, we find the tangent. That's a really bad tangent, but you get the idea. And again, find 2 points. Find the slope. Are you going to have to find slope a lot of times? Yes. Get better at it. Okay, left-hand side of the second page. Can you find average acceleration from a position time graph? Cannot be done. Can't be done. You'd have to create a velocity time graph and then find it. Instantaneous acceleration also can't be done. Okay? Let's summarize velocity time graphs. If you have a velocity time graph and you're asked to find displacement, then it is the area thing. Right? And if you got more than one shape, then you got to break it into parts. Anything above is positive, anything below is negative. And make sure you remember that it's this here, right? It's between the graph and the axis. It's not below. It's between the graph and the axis. My speed okay? I'm not going too fast. If you're asked to find average velocity, how do you do that? You got to find the displacement this way, and then divide by time. Right? You find the displacement using this area method, and then divide by time. The easiest one, instantaneous velocity. That should have a number 3 on it. It doesn't. That's weird. You simply read it off the graph. It's the easiest one. Read it off the graph. Okay, velocity time. Average acceleration. If it's a straight line graph, acceleration is the slope of the VT graph. Straight line graph, so you find the slope. If it's a curved line graph, what do? Pick your 2 points, draw a line, because we're talking about average over the interval. Average, it's over that interval. And the last one, instantaneous acceleration. If it's a straight line graph, straight line graph. To find instantaneous acceleration, we're talking about at a single point, instant, right? So you take 2 points, any 2 points, and once again, find the slope. Pretty much. You got to find a lot of slope. It's a pretty steep learning curve, Jason. If it's a curved line graph, find the tangent line. Are you going to want to have all that on your cheat sheet for the test?
Yes.
For sure. Mervyn will agree, right, Mervyn? Have a good cheat sheet. Are the cheat sheets valuable to your testing, to your tests? They are. Should we see if you have a lot of cheat sheets? I know they don't, but they do give you a formula sheet. They give it to you. Let's just see. They do. A formula sheet will be given to you. There's their formula sheet. It's not, look at, there's not a lot on there, really, is there? They're pretty generic. They do give you sine, cos, and tan. I think the study sheet's a better move, don't you? Could you still, when you're in first year university, could you still make a study sheet and then just not take it to the exam? Of course you could. Would that be a valuable thing to do, Jen? Of course. Why are the study sheets a valuable skill to have? It makes you prioritize what you don't know. Write it down, you'll remember it. It's a good study activity. Okay, time for me to be quiet. You guys can now do the rest of the booklet. Okay? You can now do every single question in the booklet. I think you're going to need some time for that. Okay? I originally scheduled the test for Wednesday. I think I better push that back another day. Right? Let's say Thursday. No. Thursday, then I got to start the word problems. Okay, so Thursday. Test. Thursday. Use your time wisely. You still have a few minutes left.